Okay, so let's start our chapter 4 discussion. This will focus on the electrolyte effects now. So the topic outline for today are the following. So we will discuss first about the hydrated ion and the equilibrium system and the ionic strength, followed by the ionic activity and the activity coefficient, then its properties. Then later on, we will calculate the activity coefficients using the Debye-Uckel equation. And by next week, no, this will be an asynchronous topic. We will discuss the applications of this topic for equilibrium systems. Okay, so this last topic will be discussed next week. However, that's asynchronous, so I will upload a video that will cover the discussion of this part. Okay. So let's talk about this topic now. And why is this different with the knowledge that we had at equilibrium? Na, so the previous topic. Na. So yan, tignan natin. Okay. So what happens when you dissolve your ionic compound in water? So what happens is that your ionic compounds are turned into ions. Okay. And our ions have this hydration sphere. Okay, so what is an hydration sphere? That is a sphere at which your ion is being surrounded by water molecules. So according to this, ions and molecules in solution are surrounded by organized sheath of solvent molecules. Why? Because there is an interaction between ions and water, and that's called the ion dipole interaction, right? So water is a dipole molecule, and our ions are charged particles, so that means the two can have interactions. Okay, so suppose we have sodium chloride ions. Okay, so sodium is positively charged, chloride is negatively charged. So how will the ion be surrounded by the solvent molecules? Okay, so for sodium, the positive charge of the sodium will attract the partial negative oxygen of the water molecule. So that means the water molecules that will surround the sodium will look like this. Their oxygen will be pointed towards sodium, as the oxygen has a partial negative charge character, which is attracted to cations. Okay, so this is how our sodium ion looks like when they are dissolved in water. They have this hydrated sphere. Okay, they have this sphere wherein they were surrounded by water molecules. Okay, the oxygen part is pointed towards the sodium, as oxygen has a partial negative charge. No? They are attracted because they have the opposite charges. Okay. Similarly, chlorides are also surrounded by water molecules. The partial positive end of the water molecule will be attracted to chloride, as it is a negatively charged particle. Okay. So, yan. So, counterpart siya ng kay sodium. No? So, instead of oxygen pointing towards chlorine, we have the hydrogens pointing towards the chlorine ion. Okay, so this is how the hydration sphere of chloride ion looks like. Okay, so again, why do we have hydration sphere? Because we have interactions of our ions and the solvent molecules. Okay, the interaction between them is called the ion dipole interaction. Okay, the smaller highly charged ions bind more water molecules and behave as larger species in the solution. So that means the size of the hydration sphere may vary depending on the charge of your ion. Suppose your ion is highly positively charged, then that means it will attract more water molecules around it. So its hydration sphere will be bigger. Okay? So in this picture here on the right side, we have different hydration spheres of different ions. Observe that if the charge is big enough, the hydration sphere gets bigger as well. Okay? And depending on the size of the hydration sphere, the activity of your aqueous solutions is related to that now. So the activity will tell us um, what will be the behavior of our ions in our solution. Okay, so that's the activity of the ions, their behavior in the solution. Okay, so how is this related in our previous topic, the equilibrium topic now? So as you can still remember, last time we were able to cover the common ion effect. No? So according to common ion effect, if you have ions that are common in your solution, what happens in reality is that their hydration sphere pushes this equilibrium to the left. No? So if you have common ions in your product, it will shift the equilibrium to the left as the hydration sphere will push back the reaction. Okay. However, there is another case in which the equilibrium is shifted, but there are no common ions. No? So, so look at this graph here. So we have an equilibrium solution of iron and thiocyanate ion producing FeSCN2 plus. Okay. The equilibrium constant is written as this. Okay. And this is the graph of the reaction quotient or the equilibrium constant. Okay. So what happens here is that suppose the initial equilibrium constant for this solution is around 275. Okay. But when inert salt such as potassium nitrate is added, when we add inert salt, what happens to the equilibrium? It begins being shifted to the left. Okay. So the equilibrium constant is now being shifted to the left when we add potassium nitrate ion. Okay. So the question there is why? No, why is the equilibrium being shifted? No, despite that our ions that has nothing to do with the inert salt. No. So as you can see, what are the ions that we can produce here from potassium nitrate? So for potassium nitrate, we can produce potassium ion and nitrate ion. Are the two ions written in our equilibrium equation? They are not. However, even though they are not written in the equilibrium equation, they can still change the equilibrium constant. Okay? They can still shift the equilibrium. So that is one of the many questions that scientists had that time. Okay, and actually this topic is just a recent discovery. Okay, so this was discovered around 1940s. No? So they were asking why, no? Because what is the relationship of these other ions with your equilibrium system? According to common ion effect, if you have added ions that are common to this equation, it can shift the equilibrium. But in our case, we do not have any ions related to our equilibrium system, but it still shifted the equilibrium. Okay, so that's one thing that puzzled scientists before. Okay, so this graph was actually published by Stulsberg in his paper in Journal of Chemical Education in 1999. No? On the other hand, no, on the other spectrum, suppose you have a precipitate. Okay, okay, so this is a precipitate, calcium sulfate. Okay, so calcium sulfate dissociates into ions as calcium 2 plus and sulfate ions. Okay, however, according to its KSP, the solubility product, okay, it tells us that the reaction here is strongly reactant. So that means only few of the ions will be produced. Okay. So that means the precipitate will predominate the solution, not their ions. Okay. On this example naman, no. So suppose they added the same salt, potassium nitrate. What happens to the equilibrium system when you add the salt? So according to observations, and actually this can be done in the laboratory, when they add potassium nitrate or inert salts, that means salts that do not react with our ions, okay? When you add inert salts in your reaction, what they notice is that when you add inert salts, the solubility of the precipitate increases. Okay, this can be done in the laboratory. Suppose you have a test tube with precipitate, which is color white. No, when you add ions, the white precipitate slowly vanishes. Okay, so that means when you add inert ions, the equilibrium is shifted again. In our case, to the right. No, so that's one of the biggest question analytical chemists had before. Why is that when we add other ions, okay, when we add inert ions in our equilibrium systems, the equilibrium constant is being shifted now. So that puzzled them actually. Okay. So at this example, the equilibrium is shifted to the left, okay, because the addition of inert salt reduce the equilibrium constant. Okay, bumaba yung constant natin. And on the other hand, if you have a precipitate, you add an inert salt, the equilibrium is actually shifted to the right, no? Wherein the solubility of your precipitate increases. That means more ions are produced from your precipitate. No? So that's one thing that puzzled scientists before. How come that inert ions can affect the equilibrium system despite that they are not written in the equilibrium constant? Okay. So upon certain investigations about the characteristics of our ions in our solution, they came up with this idea, the ionic strength. Okay. So according to them, this is the plausible answer for that, no? Why inert ions affect the equilibrium systems. Okay, so recall that our ions, when they are dissolved in water, they have this hydration sphere. The hydration sphere is also called the ionic atmosphere. So this is the atmosphere at which your water molecules or other ions can disperse into. Okay. So in our case, so let's use calcium sulfate as an example. Okay. So suppose we have the sphere of calcium ion and sulfate ion. So let me draw it here. So suppose we have a sphere for calcium ion and sulfate ion. The reason why they turn back into precipitate is that when their ionic sphere comes together, they reform the solid precipitate now. However, according to this problem, when we add inert salts, what happens is that we produce more ions instead of them going back to the precipitate form. Okay? So, how is that possible, no? So, according to this idea, ionic strength, when we add ionic compounds, they actually offset the charge of our cations that prevent them to stick together. Okay, so suppose we added potassium nitrate in our solution. What happens in reality is that potassium nitrate will diffuse into the ionic atmosphere of calcium and sulfate ions. Okay, so remember that if the calcium and the sulfate ions are alone in the solution, they will come back, no, together to form the precipitate. However, in the presence of inert ions, okay, for example, potassium nitrate, that tendency of them coming back together will be decreased. No? So, how is that possible? Okay. So, what they visualize is this. No? So, we have potassium ion from our inert salts. What will happen is that the potassium ion will flood the ionic atmosphere of sulfate ions. Okay. So, potassium ions will flood the ionic atmosphere of your sulfate ion. Okay, so they will flood the surroundings or the ionic atmosphere of the sulfate ion. So what will happen? So the overall charge of this sphere will be reduced now because majority of its charge will be now bounded to the potassium ions now. So that means the charge of this ion will be partially offset now, or the charge of this ion will decrease totally because of the presence of the counter ions. Okay. How about calcium? So we have nitrate ions from our inert salt. What will happen is that nitrate ions will flood the atmosphere of calcium. So, okay, so nitrate ions will start flooding in your um, your calcium hydration sphere. Okay, so what will happen? Okay, so what will happen is that since we have inert ions dissolve into the ionic atmosphere of our precipitates, their tendency of coming back together will be decreased significantly. Okay, because there are other ions around them, so that prevents them from sticking back together, and that's why for our example here, that's why our precipitate solubility increases now when we add inert ions. So again, why? Because inert ions provide a shield no, that prevents the two ions from reforming the reactant, no, from reforming the precipitate. So they shield the two ions so that they will not form the precipitate again, or the reverse reaction will not occur. So only the forward reaction will be possible. So that's why the solubility of the precipitate increases when we add inert salt. That's the idea of ionic strength. The more inert salts you have, the more chances that your precipitate will be more soluble. Okay? So again, imagine your nitrate ions and your potassium ions are distractions for calcium and sulfate from coming back together. Okay, so they provide distraction so that they won't stick together. Okay, to form the precipitate. So this phenomena is called the salt effect or the electrolyte effect. No, so in summary, we can describe it here. So if we have higher ionic activity of our solution, that means we have high concentration of inert salts. What will happen is that more ions will start diffusing into the ionic atmosphere of our precipitate ions. Okay? Once more ions dissolve in the ionic atmosphere, the the charge of the ions of the precipitate will start decreasing. Okay? And as a result, there will be less chances for them to produce the precipitate. And finally, the solubility will increase, or the chances of producing precipitation will be reduced. Okay? So that's the overall idea for the ionic strength. Okay? So again, the more inert ions you add in your solution, the more diverse ions will flood your ionic atmosphere. And since you have more diverse ions in your ionic atmosphere, the lesser chances for your precipitate to reform. Okay, so they will have lesser chances of coming back together. And as a result, your precipitate will be more soluble, or your precipitate will no longer form now. So it will only produce the ions. Okay. That means the solubility will be increased. Okay. This phenomena is called the salt effect now. So if we look at this graph here, uh, okay, so according to this slide, the greater the ionic strength of the solution, the higher the charge of the ionic atmosphere now. So that means the more shifted your equilibrium system will be when you add inert ions. Okay, so suppose we have this precipitate. So we have potassium hydrogen tartrate precipitate. So it will produce hydrogen tartrate ions and potassium ion, but to a very low extent. No? And here are the graphs when we added other ions, no, in our solution. Okay, so suppose that if we have this equation alone, the equilibrium constant is 0.03. Look at what happens when we add other ions. The equilibrium constant started to shift away from 0.03 when we add magnesium sulfate, sodium chloride, and potassium chloride. So the equilibrium starts to change when we add these other ions. However, for glucose, that's stagnant. So let's explain why. Okay. So for magnesium sulfate, the solubility of the precipitate increases. No? So when we say the solubility of the precipitate increases, that means the equilibrium constant of this reaction starts to increase. Okay. So that means more product will be produced. No? So when we add magnesium sulfate to this solution, the solubility of the precipitate increases. Why? No? Because we assume that these ions serve as the shield for the products. Okay. They provide shield for the products so that they will not come back together to form the reactant. Okay, so magnesium ion will flood the tartrate ions. Sulfate ion will flood the ionic atmosphere of potassium ions. So since they are now shielded, they will not come back together to reform the reactant. No. So they will not come back together to form the precipitate again. As a result, their solubility will increase now. So more ions will be produced because there is a lesser chance for them to go back as precipitates. Also, for sodium chloride, what we can see here on this graph is that the solubility also increases. However, the increase in the solubility is lesser than that of magnesium sulfate. So the reason why the solubility of this precipitate increases is because of the presence of inert salts such as sodium chloride. What happens is that sodium ion will flood the ionic atmosphere of the tartrate ion, and chloride ions will flood the atmosphere of the potassium ion. So since they are now shielded, the reverse reaction will not occur. Okay, so that means these two ions will no longer come back together to reform the reactant. Okay, so that means only the forward reaction will be favored when we add the inert salts. Okay, so as you can see, the effect of sodium chloride is lesser than magnesium sulfate. Why? Because magnesium has higher charge. No? So according to this, the greater the charge, the greater the ionic strength. No? So that means the more shielding happens. No? How about glucose? No? For glucose, the solubility of our precipitate is stagnant at 0.03 molar. So why is it stagnant? Because glucose is not a charged particle. So that means it will not flood the ionic atmosphere. Okay? So if we have uncharged particle, for example, glucose, they will not flood the ionic atmosphere. Hence, they do not have ionic strength, or they will not flood into the ionic atmosphere. No? Because they don't have charges. No? So that's why the solubility is stagnant. Okay. On the other hand, let's have potassium chloride. When we add potassium chloride in our equilibrium system, what happens? The solubility decreases. So the decrease in the solubility means that the reaction is shifted to the left. Why? This is governed by the common ion effect. No? So when you add KCl in your solution, remember that we also have potassium ions on the product side. So we now have common ions. Since we add more of the products, according to Le Chatelier principle, it will shift the reaction to the left. Okay. So increasing the concentration of potassium will shift your equilibrium to the left. Hence, the solubility will decrease because more precipitates will be formed now. Okay. So that's the reason why we have this trend on our graph here. When you add inert salts, they provide shielding so that your ions will not reform the precipitate. However, when you add common ions, they will push the reaction backwards. Okay, so they will push the reaction to reform the precipitate. Hence, the solubility of the precipitate will decrease. Okay, and for uncharged species, it has no effect, no, because it doesn't have any ionic strength. No. So for uncharged species, they will not flood the ionic atmosphere of your ions so that they will have no effect. No. Okay, so that's the idea lang. No. So that's their recent discovery. No. So this was actually published in 1998. No. So again, what's the essence of this topic? So the essence of this topic is that we are now able to tell that inert ions can really change the equilibrium system, despite that it is not written on our equilibrium expression. So magnesium sulfate, it is not written on the equilibrium expression, but it can shift the system. It can shift the system now. Why? Because they actually flood the ionic atmosphere. Okay, so they flood the ionic atmosphere that prevents the precipitates from reforming. Okay, so how do we measure the ionic strength of the solution? Okay, because this is important later on. For us to measure the ionic strength of the solution, that is the strength of our diverse ions, we use the formula mu is equals to 1/2 of the sum of the product of the charge squared and the molarity. So suppose you have a diverse ion solution. In order for you to get its ionic strength, you multiply the molarity of your ion times its charge squared, and then you add all of them. Okay, and then you multiply them later on by 1/2. Okay. So again, X is the molarity and Z is the charge of your diverse ions. Okay. So suppose we have the following solutions. Let's find their ionic strength. So for number 1, we have 0.1 molar sodium nitrate. Okay. So what happens to this diverse ion? What happens to sodium nitrate when we dissolve this? It dissociates into sodium ion and nitrate ions. So it will start dissolving into ions. Okay. That is a full dissociation process. Okay, so if we have 0.1 molar of sodium nitrate, what is the concentration of sodium and nitrate ions? Okay, the concentration of sodium and nitrate ions can be determined by their stoichiometry. Okay, so if their coefficients are the same, that means their concentration will be the same. Okay. Okay, so that means if we have 0.1 molar of sodium nitrate, we will produce 0.1 molar of sodium ion and 0.1 molar nitrate ions. Again, when their coefficients are the same, we will have also the same concentration. Okay. So now we know the concentration of the ions. We have 0.1 molar sodium and 0.1 molar nitrate ions. Let's now solve for their ionic strength. Okay. The formula for ionic strength is 1/2 the sum of the concentration of your ions times their charge squared. Okay. So for our ions, let's write the mu expression or the ionic strength expression. So that can be written as 1/2 times the concentration of sodium ion and the charge of the sodium ion squared plus the concentration of nitrate ion times the charge of the nitrate ion squared. Okay? So after writing the expression for solving mu, we can now plug in our available data in the equation so we can solve for mu. Okay. So what is the concentration of sodium ion in our solution? Sodium is 0.1 molar. Okay. What is the charge of sodium ion? The charge of sodium ion is positive 1, of course. So the z squared will be positive 1 squared. About nitrate ion. So for nitrate ions, the concentration is 0.1 also. And the charge of the nitrate ion is negative 1. We're going to get the square of negative 1. Okay. So what is our mu or the ionic strength now? So the ionic strength can be calculated as this. You can do this mentally. So what is 1 square? So that's 1. So 1 times this is 0.1. What is negative 1 squared? That's also 1 times 0.1. So that is also zero point 0.1. Okay, so we have 0.1 here, 0.1 there. If you add them, you will get 0.2. You divide them by 2. So overall, the ionic strength is 0.1 for this solution. Okay, you can type this in your calculator or you can solve for it mentally. Okay, so that is the ionic strength of this diverse ion solution. So let's try the next item. No? Okay, so let's try the other items. So let's try to determine the ionic strength of sodium sulfate solution. Okay, so let me erase this part here. Okay, so if we have sodium sulfate in our solution, it will dissociate into its ions. Okay, so what will be the products? So we will produce 2 moles of sodium ion and 1 mole of the sulfate ion. Okay, so again, 2 moles of sodium ion will be produced. Why? Because we have to follow the law of conservation of mass. If you have 2 sodium atoms on the reactant side, then that means you must also have 2 sodium ions on the product side. No. So whatever your subscript is, it becomes the coefficient when it turns into ions. Okay, so you just follow your stoichiometry here. If we have 0.01 molar sodium sulfate, what will be the concentration of your products? Okay, so the concentration is proportional to your coefficients now, because we still follow the law of conservation of mass. So according to this equation, we will produce 2 moles of sodium. So that means we will produce twice the concentration of your original ion. Okay, so whatever the coefficient is, you multiply it with your concentration. Okay, so that means we will produce 0.02 molar sodium ions. Okay, the concentration will be twice that of the original concentration because of the coefficient. How about sulfate ion? So sulfate ion has the same coefficient with sodium sulfate, so that means they will have the same concentration, 0.01 molar. So again, when you have coefficients, you multiply it with the original concentration to get the actual concentration when that ion is dissolved. So now we have the concentrations of our ionic species. We can now plug it into our formula for ionic strength. So that's mu equals 1/2 the concentration, the sum of the concentrations times their charges squared. So let's write the mu expression for this problem. So mu is 1/2 the sum of the molarity and the product of charge of sodium and sulfate ion. So for sodium, we write this as the square bracket of sodium times the charge of sodium squared. And for sulfate, we write it as the concentration of the sulfate ion times the charge of the sulfate ion squared. Okay. So basically, whatever is in your product side, you're going to plug it into your terms here. Okay. So the concentration and their charges has to be multiplied. And then you're going to add them together. So let's plug in our info. Let's plug in our given numbers. The concentration of sodium is 0.02. What is the charge of sodium ion? It is positive 1 squared. And then for sulfate ion, its concentration is 0.01 molar times the charge of the sulfate ion is -2. Then you're going to get the square of it. So mu is 1/2. What is 1 squared? That's 1 times 0.02. So that will be 0.02. Plus we have -2 square. So that will be 4 times 0.01. We will have 0.04. So if we multiply the sum of this by 1/2, we will get 0.03 molar. So this is the ionic strength of our solution. 0.03 molar. Okay, so the sum is 0.06, but you have to multiply it by 1/2. No? So you have to divide the number by 2. You will get 0.03 as your ionic strength. Okay. Let's try number 3. So for number 3, we have two diverse ions. Okay, so we have two diverse ions for number 3. Okay, so let us show the dissociation of those ions and their corresponding concentration. So for potassium bromide, it will dissociate as K plus and Br minus. For sodium sulfate, it will dissociate as 2 moles of sodium ion and 1 mole of sulfate ion. So we have 0.02 molar of KBr. What will be the concentration of K plus when it dissociates? So it will be just the same. And same for bromide ion. Because their stoichiometry are all equal. Okay. They all have a coefficient equal to 1. So that means their concentrations will be equal. Okay. How about sodium sulfate? Okay, so for sodium sulfate, we have 0.01 molar. Okay. We will produce 0.02 molar of sodium ion and 0.01 molar of sodium sulfate. Okay. So to get the overall ionic strength of two ions, we will add the ionic strength of KBr and the ionic strength of sodium sulfate. Okay. So lucky for us, we were able to solve for the ionic strength of sodium sulfate. So we are now just looking for the uh, ionic strength of KBr. So let's solve for this first now, because we already have the ionic strength for sodium sulfate. Okay. So to get the ionic strength of KBr, it's 1/2 the concentration of K plus times the charge of potassium ion squared plus the concentration of bromide ion times the charge of the bromide ion squared. So that will be 1/2 the concentration of potassium is 0.02 Charge of potassium is positive 1 squared. The concentration of bromide is 0.02 as well. Charge is negative 1. Then you get the square. So overall, the ionic strength of KBr solution will be 0.02 molar. Okay? So all of this is equal to 0.02 molar. And then, to solve for the overall mu of the solution, so that is the sum of the mu, or the ionic strength of potassium bromide, and the ionic strength of sodium sulfate. So the ionic strength of KBr is 0.02 molar, and for sodium sulfate, that is 0.03 molar. So overall, the ionic strength of this mixture will be 0.05 molar. Okay. So why do we have to determine the ionic strength, no? Because according to the previous slides, when you increase the ionic strength, that means the effect of electrolytes increases. Okay. That means the more shifted our equilibrium becomes, no? So this is analytical chemistry. If we want to quantify stuff, then we have to measure everything, okay? So since we want to measure the changes in the equilibrium expressions or the equilibrium constant, that means we have to solve for the ionic strength, okay? So later on, we will use this ionic strength um, to get the actual effect in our equilibrium systems, okay? So that's how you solve for ionic strength. The greater your ionic strength, the greater the electrolyte effect. Okay. So that means for precipitates, more products will be formed now when you have ionic strength that is very high. Okay. Okay. So going back to our equilibrium systems, if you could still remember, our equilibrium equations are written in terms of the concentrations. No? So we have the concentration of the products divided by the concentration of your reactants. However, according to our topic today, even though the concentration of diverse ions are not written here, they can still shift the equilibrium constant. So that means we are missing something, okay? So that means our equilibrium constant is not the actual uh, that is not the actual way to solve for the equilibrium systems, no? Because it disregards the effect of diverse ions. So that's why they came up with this activity, letter A. Okay. So that's what they came up with activities. No? Okay. So what is activity? So activity takes into account the effect of the diverse ions. Okay. So activity refers to the behavior of the ionic atmosphere. No. If it is clear or it has diverse ions in it. No. So activity takes into account those effects. No. Especially the diverse ions. No. Okay. So according to analytical chemists, so instead of writing K in terms of concentration, we can just simply write K in terms of activities, not of concentration. Because if we just write the concentration, we are neglecting the effect of diverse ions. However, if you write activities, then the effect of diverse ions will be accounted. Okay? So, yan. So, the effect of the diverse ions will be taken into account when solving for K. So, we can totally explain now why K is shifted when we add diverse ions. Okay? So, again, why K is shifted when we add diverse ions? They change the activities of our our ions in the equilibrium system. Okay, so how do they change the activity of our ions in equilibrium system? They disperse into the ionic atmosphere. Okay, so that the overall charge of the ions decreases. No, so that phenomena, the decrease in the overall charge of our ions in equilibrium, that is the activity of the ion. Okay, so again, instead of writing the equilibrium constant in terms of concentration to account for the diverse ion effect, we use activities now. So they just found out that this is too idealistic. The actual one is in terms of activities of the product and the activities of the reactant. Okay, so activity is equal to the concentration times this term gamma. Okay, so what is gamma? Gamma is the activity coefficient. Okay, so let's focus on gamma. Okay, because we already know the concentration. So what is gamma? Okay, so gamma is a measure describing the departure of your ion from its ideal behavior. Okay, so without the diverse ions, your gamma is equal to unity. So that means it is equal to 1. However, when we add diverse ions, gamma decreases or gamma departs from its ideality. Okay. So suppose you have a solution without diverse ions, you are okay to write the K in terms of concentration because gamma is equal to 1 without the diverse ions. Okay. However, if you take into account the diverse ions, then you have to include that in your calculation. So you're not going to write the concentration alone. Instead, you also have to multiply the activity coefficient gamma. Okay, because this will tell you what will be the effect of the diverse ion to your species now. To what extent will the charge of that species decrease now? So gamma is that measure. Okay. So in order for us to express the effect of ionic strength on the calculation, we calculate the activity by multiplying the activity coefficients. Okay. So this is the coefficients that take into account the effect of salts, no, of diverse ions. Okay. So yan. So that means the correct way to write equilibrium for a generic reaction AA plus plus BB in equilibrium with C and D. Teka lang. So for this generic equilibrium expression, the actual equilibrium constant considering the effect of diverse ion is written as the activities of the products over the reactants. That is the activity of C raised to its coefficient times the activity of D raised to its coefficient, all divided by the activity of A raised to its coefficient and the activity of B raised to its coefficient. So compare that with our method of writing the equilibrium constant on the last chapter. On the last chapter, we just write the concentrations. But this time, since we are taking into account the effect of electrolytes, no, of other ions, so we have to use activities instead of just concentration. Okay. So we use this equation when we have diverse ions. However, if we do not have, then you can use the traditional equilibrium equation. So we know that activity is equals to gamma times the concentration. So we can expand this equation as this. So the activity of C can be written as the concentration of C and the gamma of the C. And the same is true for other species here, okay? So you're just going to substitute this into your activities. So you will get this form of the equation. And also, remember that when you combine your concentrations, that will give you the original K. That will give you the original equilibrium constant. Okay. So that means the new equilibrium constant is just the typical equilibrium constant multiplied to the gamma or to the activity coefficients. Okay. If you multiply your K with gamma, its value will decrease. Hence, or it may decrease or increase. Hence, your K will change now. Okay. So gamma can increase or decrease your original K value when you multiply it into the K. So suppose we have this reaction here. So this is the dissolution of calcium sulfate into ions. The former way of writing the equilibrium constant is just this. No? So that is just the concentration of product, nothing on the reactant because the reactant is solid. So this is the conventional way of writing the equilibrium constant. But now, since we have to take into account the effect of the other ions, we use K prime. So K prime makes use of activities instead of concentration. So K prime can be solved as the activity of calcium and the activity of sulfate ion. And we know that activity is equal to concentration times the gamma. So we can express this as the concentration of calcium times the gamma of calcium. And this one can be written as the concentration of sulfate times the gamma of the sulfate. If you combine the concentration, you will get your original K. No? You will get your original equilibrium constant. So we can write it as KSP. Okay. By the way, the equilibrium constant for precipitates, they are called KSP or the solubility product constant. Okay, that will be discussed in your laboratory. So your lab instructor will focus on this one. Okay. So KSP is the solubility product constant or just the K, for precipitates. So again, if you combine the concentrations, you will get your original K expression times the gammas, okay, times the activity coefficients. Okay, so let's try to answer this problem. Okay, so let us write the solubility product expression for lanthanum 3 sulfate with activity coefficient. So before we can start writing the solubility product with activity coefficients, we have to write first the dissociation reaction. Okay, so let's write the dissociation of this ion. No? So we have La2SO4 3. If you do the reverse crisscross, okay, reverse crisscross will tell you that lanthanum is 3 plus in charge, 3 plus in charge, and sulfate is negative 2 in charge. No? So you will get 2 moles of lanthanum 3 plus and 3 moles of sulfate ion. Okay. So we obtain the charges by doing the reverse crisscross. However, the coefficients are determined by their subscripts. So we have 2 moles of lanthanum, so we'll get 2 La. We have 3 of the sulfate, so we will have 3 sulfate ions. So let's write the KSP for this equation, the typical K. So if we write the KSP, that is just the concentration of the products divided by the reactants. So that will be the concentration of your products, lanthanum 3 plus squared, and then you have sulfate ions cubed. Okay, so this is the K expression. Nothing will be written on the denominator as the denominator is a solid. Okay, so that's the KSP. How about if we write the KSP with activity coefficient? So that means we are now looking for K prime. So for K prime, that is similar with our original K. However, instead of uh, writing the concentrations, we write the activities. No? So we write it as A lanthanum 3 plus squared times activity of sulfate ion cube. Okay. So again, the only difference is that instead of writing concentration, square brackets, we write letter A. That means we are talking about the activity of the ions in our K prime. And we know that activity is equals to concentration times the gamma. So let us substitute that in our equation. K prime can be written as the concentration of lanthanum 3 plus squared times gamma of lanthanum 3 plus squared. So you distribute the exponent now. So if A is squared, then your concentration will be squared and the gamma will also be squared now. So we distribute the exponent. How about sulfate? So we can write the activity of sulfate equal to the concentration of sulfate ions cube times the gamma of sulfate ions cube. Okay. If we combine the concentrations, we can rewrite this equation as K prime equals KSP times the gamma of lanthanum 3 plus squared and the gamma of sulfate ion cube. Okay, so these are two ways no, to write the solubility product with activities. So you can use this or you can use this now. So on this part, we just combined the concentration as the KSP. Okay. And then we excluded the gammas now. So how about here for this one? We have copper 3 sulfate. Okay, so this is uncommon ion. Hindi siya widely used, no? Because copper is usually positive 1 and positive 2, no? But in our case, copper is positive 3 in charge. So this is quite weird. So let's write the dissociation of this precipitate into ions. So we have Cu2SO4 3. So if you do the reverse crisscross, you can determine the charges of your ions. So this 3 came from copper. So the original charge of copper is positive 3. And for sulfate, that's negative 2. So why do we denote the charges? Because this is important uh, for solving the ionic strength, just in case lang. Okay. For you to be reminded of how to determine the charges. Okay. So this is just a reminder how to get the charges. Okay. Because that's important when you solve for the ionic strength, diba? It includes the charge squared. So let's write the dissociation of this salt into ions. So we will get 2 moles of copper 3 plus and 3 moles of sulfate ions. We write the KSP for this equation. That's the typical that's the typical K expression in terms of concentration. So we will get copper 3 plus squared and sulfate ion cube. However, if we write the solubility expression with activity coefficient, that means we are pertaining to K prime. So K prime is similar with our KSP, the original K. However, instead of writing concentrations, we write the activities, letter A. So that's the activity of copper 3 plus squared times the activity of sulfate ions cubed. And then we plug in the equation for activity, that's concentration times the activity coefficient, gamma. So we plug it into our A. So we will get concentration of copper 3 plus squared times gamma of copper 3 plus squared as well. Then for sulfate, that's the concentration of sulfate cube times the gamma of sulfate cube. If we combine the concentrations, we can simplify this equation as K prime equals KSP times gamma of copper 3 plus squared and gamma of sulfate ion cube. Okay? So these are the two ways of writing the equilibrium constant. So you can write your concentration and gamma, or you can just combine your concentrations as KSP. But I prefer writing this one here, the second line, okay? Because it shows us the concentration expressions, okay? Although you can rewrite this as KSP naman, okay? So that's how we write the equilibrium constant now, okay? So why do we have to change the equilibrium constant ulit? Why do we have to change the way we write equilibrium constant? That is because we want to include the effect of diverse ions, no? Our original K doesn't include the effect of diverse ions. So that if we want to include that, we have to use activities, no? So we have to change the way we write the activity. Okay. So the common question in mind is this the way that we're going to write the equilibrium constant starting from now? Okay, so ito na ba yung way natin ng pagsusulat ng case starting ngayon? So the answer is no, no. So we are just going to write the K as this for this chapter. However, in the future chemistry chapters, chapter 5 to 8, no, we are going back to this K expression. Because on this chapter, we are just trying to explain the effect of other ions, no. But for the next chapters, we're going to neglect the effect of other ions na lang. Okay, so we're going to neglect them. So that means we are not going to use activities for the next chapter, only for this chapter. Okay? Yan. Baka kasi isipin nyo hanggang dulo, ganito na tayo, no? No. We're trying to simplify things, no, in the future. But for now, we will do this as is, no? Ganyan talaga siya. Okay, so let's talk about the properties of activity coefficients. Okay, so again, the activity coefficient, this is the measure of the effectiveness of your species, no? As it influences an equilibrium system. In dilute solutions, your activity coefficient is unity. So that means if you have small amounts, very small amounts of diverse ions, then you can say that the activity coefficient is equal to 1. So if gamma is equal to 1, then activity is equal to the concentration na lang. Okay? Okay. Activity will be equal to concentration. So that's why we write equilibrium constant in terms of concentration, because we assume before that gamma is equal to 1. However, in our case, gamma is equal to something else. So we have to include gamma now. Okay, so yan. So activity coefficient will tell you the effectiveness of your species. And when you have dilute solutions, the constant is unity, or that is equal to 1. Okay. Because if you add diverse ions, remember that the ionic atmosphere changes. So that means gamma will decrease now. So yan, that's why we have to take into account for gamma in this chapter. Number 2, in solutions that are not too concentrated, the activity coefficient is independent from the nature of electrolyte and dependent only on the ionic strength. So there is an equation for this one. We will discuss this later on. Next one, for a given ionic strength, the activity coefficient of an ion decreases dramatically from unity as the charge on the species increases. So that means the greater the charge of your diverse ions, okay, or the greater the charge of your chemical species in equilibrium, the greater the effect will be on the activity coefficient now. So the greater the charge of your species, the greater the decrease in your activity coefficient from unity. So it will be less than 1 dramatically. Okay. For number 4, the activity coefficient of uncharged molecule is 1. Okay, so that means if you have added solution, if you have added molecules that are uncharged in your solution, then your gamma is equal to 1. Hence, equilibrium constant will not be shifted. So this explains why we have this graph earlier. So in our graph earlier, we shown that when we add glucose, K is not changed, no? Because gamma is just 1. So that means K prime here is just K. Okay, because gamma is equal to 1 when we add uncharged species. So that's why the solubility is constant. However, for inert salts, then your K prime is less than the K because we need gamma. Okay. And then for common ions, that is actually governed by uh, Le Chatelier principle. Okay. So this one is already governed by Le Chatelier principle na. Although you can still use K equals K gamma. Okay. So you can use this one pa rin. Because remember, KCl is also a salt. No? It has an ionic activity pa rin. Okay, so again, when you add uncharged species, your gamma is unity. So that means gamma is equal to 1. That's why the solubility of this precipitate is unchanged when you add glucose kasi whatever your K is, if you multiply it by 1, that's your K prime then, okay? So K doesn't change in reality, no? At any given ionic strength, the activity coefficient of ions of the same charge are approximately equal, okay? So that tells us that for for ions with similar charges, gamma is almost the same, although there are variations because of the size of the ionic atmosphere or this diameter of your hydrated ions. Now, we already know the behavior of activity coefficient gamma. So for dilute solutions, gamma is equal to 1. However, if we increase the charge of our species, gamma will be less than 1. Or if we increase the ionic strength of the solution, gamma will also be less than 1. Okay? So the question here now is, what is gamma? Okay? How to solve for the activity coefficient? Okay? So we already know its effect on the equilibrium equation, but how do we measure it? No? Because it has a numerical value other than 1. Okay? So to solve for gamma, we use this equation. Bulaga, di ba? The Debye-Uckel equation. So the Debye-Uckel equation, this is an equation which relates the effect of the charge, the ionic strength, and the hydration sphere to your gamma value. All of them play a role to what the value of gamma will be. Okay. So your charge, your Z, your ionic strength, your mu, and your hydration sphere, the alpha, they all affect, they all have an effect to your gamma. Okay, so if the charge increases, gamma will decrease. Okay, if the mu increases, the gamma will decrease, and so on and so forth. Okay, so that means that in order to solve for gamma, we have to use this equation. Okay, okay, so yeah. So again, Z is the charge of your species of interest. Mu is the ionic strength that we already solved before, and alpha X is the diameter of your ions. Okay. However, we can reduce that equation if the mu is less than 0.01. So we can reduce this term as this. Negative log gamma equals 0.51 z squared times mu. Okay, so this is called the Debye-Euckel limiting law. Okay, and that is the reduced form of the Debye-Euckel equation when your solution is slightly dilute. Okay, so we can use the two equations to solve for gamma. Okay, so if your ionic strength is greater than 0.01, then you have to use this. However, if ionic strength is less than this, if that is less than 0.01, then we can use uh, the limiting law, the DHLL. Way, the diameter, the effective diameter of the hydrated ion, that is the ionic atmosphere, that is in units of nanometers. Let's try to work on this problem now so that we can appreciate the Debye-Euckel equation. So let's try to find the activity coefficient of hydronium ion H plus in 0.05 molar sodium chloride solution, given that the ionic radius of H plus is 900 picometers. Okay, so before you start using the Debye-Euckel equation or the Debye-Euckel limiting law, you solve first for the ionic strength. Okay, so that's the typical first step. Okay, so you solve for mu first. So again, mu is the half of the sum of the charges times the concentration. For NaCl solution, let us write the dissociation. We have Na plus and Cl minus. If we have 0.05 molar of NaCl, what will be the concentration of the other ions? That will also be 0.05 molar. Okay? So let's plug it into our mu equation. So mu is equals to 1/2 times the concentration of sodium ion times the charge of the sodium ion square. Concentration of chloride ion times the charge of the chloride ion squared. So that is 0.05 molar times, what is 1 squared? Okay, that is also 1. Okay, and then we have the chloride ion concentration, still the same, multiplied by -1 squared. Okay, so this is -1 squared, so that's just 1. So 1 times 0.05 is 0.05. 1 squared is just also 1 times 0.05, that is also 0.05. So you add the two 0.05, you will get 0.1. Okay, you divide it by 2, you will go back again to 0.05. So this is the ionic strength of our solution. Okay, so that is the ionic strength of our solution, 0.05 molar. So let me write it here. So since we are able to solve for the mu, we can now solve for the gamma, the activity coefficient, using the Debye-Euckel equation. We will not be able to use the Debye-Euckel limiting law because the concentration, I mean activity coefficient is greater than 0.01. We have 0.05, so we will not use the limiting law. So we will just use the generic Debye-Yukel equation. Okay. So what is the generic Debye-Yukel equation? So that's negative log of gamma x equal to 0.51 zx squared times the square root of mu divided by 1 plus 3.3 alpha x times the square root of mu. Kailangan kabisado? Hindi naman. Nakabisado ko na lang. Okay? So that is our Debye-Yukel equation. Take note that Z is the charge of your X, mu is the ionic strength, and alpha X is the hydration sphere. Okay, the ionic radius. Okay, so our ion of interest is H plus. Okay, so we are looking for the gamma of H plus. So that means all the X values here has to be replaced by H plus. Okay, so yan. Just take note that X here is equal to H plus. So if you want to solve for gamma, and that is inside the logarithmic function, what will we do? In order to remove the gamma from the log function, you have to do the anti-log, okay, the anti-logarithm of this equation to solve for gamma. So how can we do that? Okay, so for negative sign, you transpose it on the other side. Transpose it on the other side. Okay, so we have the negative sign on the other side already. And now we can do the anti-logarithm. Okay, so that means we will make our equation the exponent for the base 10. We are going to plug this equation as the exponent for 10, same as here now. So we will get 10 raised to log of gamma x equals 10 raised to negative 0.51 zx squared square root of mu divided by 1 plus 3.3 alpha x square root of mu. So what's 10 raised to logarithm of x? So remember that logarithm and the anti-logarithm will cancel out, okay? So 10 and log will cancel out each other so that gamma will be brought down. So gamma x equals 10 raised to negative 0.51 zx squared square root of mu divided by 1 plus 3.3 alpha x square root of mu. Umagang-umaga naggaganito tayo. Ang saya ng buhay, di ba? Okay, so this equation here, okay, this will tell us what the value of gamma is now. So what we're going to do next is to plug in whatever info we have here now. So, pa-plug in na lang natin. Okay, let's do that now. So I will rewrite this. I will erase this part muna so that I will have more space. Let me rewrite it here. So gamma can be solved as the 10 raised to negative 0.51 z squared times the square root of mu 1 plus 3.3 alpha square root of mu. Since we are looking for the gamma of H plus, that means we have to solve for the charge of the H plus and its atomic radius, ionic radius rather. Okay, so we are looking for the charge of the H plus and the ionic radius of H plus. We already know the mu. Okay, so what is the charge of H plus? Obviously, that's positive 1. How about the alpha H plus, the size of the H plus? According to this problem, that is 900 picometers. But we need nanometers because according to this slide, the diameter of the hydrated ion must be expressed in nanometers. So we convert PM into nanometers. Okay, so 1000 picometer is equal to 1 nanometer. So again, 1000 picometer is equal to 1 nanometer. So basically, we will just divide this number by 1000. So we will get 0.9 nanometers. Okay. So since we already have all the info necessary to solve for gamma, we have the mu, we have the charge of the H plus and the alpha. We can now plug it into our equation. So we will have 0.51. What's z squared? So that will be positive 1 squared. Square root of mu, the ionic strength, that is 0.05, divided by 1 plus 3.3 times the radius of your ionic atmosphere. So that's 0.9 square root of your ionic strength now. So that's 0.05. Okay, so we can now solve for gamma. So let us now solve for gamma. And by the way, this is a typographical error. So that's not radius, that is the diameter. Okay, I forgot to correct that now. Because it tells us here that it must be in diameter units now. So this is not the radius, that is the diameter. Okay, so let us type this into our calculator so we can solve for gamma times 1 square times square root of 0.05, 1 plus 3.3 times 0.9 times the square root of 0.05. So gamma is now equal to 0.85, okay, in 2 decimal places. So as you can see, because of the effect of our inert ions, because of the presence of diverse ions, NaCl, the gamma, the activity coefficient of H plus is less than 1. Okay? However, if we do not have any diverse ions, then this equation will just be equal to 1. Okay? So this will all be 0. So 10 raised to 0 is equal to 1 now. So why gamma is equals to 1 when you do not have any diverse ions. But in the presence of diverse ions, your gamma will start to decrease now. It will deviate from unity. Okay. So as an effect, no, the activity of your H plus will decrease now. Remember that the activity of H plus is the concentration times the gamma. So since we have lower gamma right now, so instead of having gamma equals 1, our activity coefficient is now 0.85. So that means the activity of H plus will decrease. Hence, the equilibrium constant will be affected. Okay. So we were now able to describe the effect of diverse ions in our problems, no, in our equilibrium systems. That is with the help of the activities. Okay. So since gamma decreased, your activity will decrease now, although the concentration is still the same. Right? That's why equilibrium constant is affected when you add diverse ions. Okay. Let's try this one. So let's just solve for the Activity coefficient of sodium ion is 0.005 molar NaCl. So since okay, so I will just give the ionic strength. So that is already equal to 0.05 molar. Okay, 0.005. You can do that mentally, no? So if you want to double check, no, you can use the equation for ionic strength. No? But you will end up with this answer. Okay. So I will assure that this is correct. I will assure you this is correct. Okay. So, yeah. So our ionic strength is 0.005. So since ionic strength is less than 0.01, we can use the Debye-Yukel limiting law. So that's negative log of gamma equals to 0.51 Zx square root of mu. So we can use the Debye-Yukel limiting law. To solve for gamma, okay, that can be solved as negative 0.51 Zx square root of mu. Okay? So mental derivation na lang, ha? So yan. Then we can plug in all our info. So since we are looking for sodium, that means we're going to assign the charge of sodium here and the ionic strength of the solution. So let's plug in our given info. That will be 0.51 times positive 1 squared, square root of 0.005 molar. Gamma for sodium ion in this dilute solution is so gamma is 0.92. It's slightly deviated from unity. No? So it will have a small effect, no, with the equilibrium constant. Okay, so you can do this derivation mentally, no? Especially if you're used to uh, derive equations na para mabilis. As you can see, when we use the Bayucal limiting law, we do not need any ionic radius, no? We're just going to plug in whatever is written, no? Okay, so ganun na lang. So that's why the Bayucal limiting law is quite handy. Okay, so the big question here is this. Are we going to use the Debye-Yukel limiting law and the Debye-Yukel equation all the time? No. Okay. Why? Because someone already did that. Okay. Someone already calculated for the activity coefficients given a certain value for the ionic strength. That means just solving for the gamma because we just want to practice the use of the Debye-Yukel equation and the Debye-Yukel limiting law. However, someone already did that, okay? So the name was Kieland, okay? So Kieland tabulated all the gamma values. So there is no need anymore to use the Debye-Yukel equation, okay? So we have here the ions and their corresponding gamma for different ionic strengths. So Kieland already did that, okay? So this paper was published in the Journal of American Chemical Society in 1937. Okay, that was before World War II. Okay, so he published this paper with the activity coefficients all written for different ions. So that means there is no need anymore to use the Debye-Yukel equation. Instead, we are just going to look for the ionic strength and compare. No, you just look for the ionic strength and then you will get the corresponding gamma value instantly using this table. So you have to save this picture. No? You have to save this table. Okay. So in our previous example, we are looking for the activity coefficient of H plus when mu is equal to 0.05. So let's look at this table. Do we have an ionic strength equal to 0.05? Yes. This is the H plus ion. Okay. So the corresponding gamma is 0.86 according to this table. Is that what we are able to solve? Yes, no. Although malapit lang, no, 0.85. But on table that's 0.86. No? That small discrepancy is okay. Okay. So that means there is no need anymore to solve for this equation. No? You're just looking to look for the mu and your species, then you will get your gamma already. Okay? So just in that instant, no, pwede mo na makuha yung gamma. How about the previous problem? So we have 0.005 molar NaCl. What is the gamma? So according to our calculation, that's 0.92. So if we look at this table by Kieland, no? So this is the 0.005 molar ionic strength. Look for sodium. Asan siya? Ito. Sodium is here, so that means the gamma is 0.928. We were able to get 0.92, which is near na. No? Magkalapit lang yung nakuha natin. So that means there is no more need to use the Debye-Uckel equation and the Debye-Uckel limiting law as long as the ionic strengths are within this range, no? Within 0.001 and 0.1 molar. Okay? As long as the ionic strength is within this range, then you can use this table. However, if you have an ionic strength greater than 0.01, I mean 0.1, or less than 0.001, if you have ionic strengths outside this stable range, then sadly, you have to use the Debye-Uckel equation. Okay. But if your ionic strength is within this range, then you can use this table. Okay. Using this table, let us calculate for the activity coefficient of K plus in 0. By the way, this is a typo error. Kasi if that's 0.5, you have to use Debye-Uckel. That's beyond the limit of the table. So, yan. So, to skip that part, no? To make things easier. So, let's rewrite it as 0.05. No? So, let's find the activity coefficient of K plus if we have 0.05 molar KCl. So, of course, you will get the mu. So that's 1/2 the charge of, the concentration of K plus, its charge square plus the concentration of chloride ion times the charge of the chloride ion squared. Okay. So if you plug in all the info, you will get 0.05 molar. Okay. Kaya niya yan i-mental. Okay. Mental math lang. If you plug in all the info from the dissociation reaction of KCl, you will get this mu. Okay. Then since we already know the mu, let's look for the gamma K plus using Kieland's table. So where is 0.05? So this is the table for 0.05 and look for K plus. Asan siya? Ito. So K plus is on this row, potassium. So that means its gamma is 0.805. Okay? So that's our answer. Tapos na. So ganun lang. Bandali. We were able to answer this problem in just few seconds, no? As long as you already know the ionic strength. You just look at this table, okay? Okay, so looking at this table, the gamma for K plus at this ionic strength is 0.805, okay? So we were able to solve for that now instantly without the use of the Debye-Uckel equation. About this one, we have to find the activity coefficient of calcium in 3.3 millimolar calcium chloride solution. Solve for ionic strength. This one, I'm not going to use mental math here. So let us show the solution. So we have calcium chloride. If this dissociates into ions, we will get calcium 2 plus and 2 chloride ions. Millimolar is just 1/1000th of the moles. Now, molarity pala, no? So that is 1/1000th of the molarity. So to convert this into molarity, because that's what we need, you just divide this by 1000. So that will be 0.0033 molar. So what will be the concentration of calcium? That will be 0.0033 molar. How about chloride? So since chloride has a coefficient equal to 2, then you have to multiply the concentration by 2. We can now solve for mu, that is 1/2 the concentration of calcium 2 plus times its charge squared plus the concentration of Cl minus times its charge squared. So mu is 1/2 times the 0.0033. The charge of calcium is 2 squared, okay, plus the concentration of chloride ions times the charge of chloride ion squared. So that will be -1 squared. Solving for mu. So let's use the calculator because this is quite difficult to work on mentally. Okay. So we have 0.0033 times 2 square plus 0.0066 times -1 square. That's equal to 0.0099. Okay. So 0.0099, or we can approximate this as mu equals 0.01. Okay, approximation is accepted here. Okay, as long as the decimal is around 9998, so on and so forth. Okay, you can approximate that to the nearest value. Okay. So the mu is approximately 0.01 molar. So since we already know the mu, let us solve for the gamma of calcium 2 plus using the table. So by the way, this table is divided into different charges. So we have the +-1 charge here, +-2 charge here, +-3 charge here, and +-4 charge here. So since our ionic strength is 0.01 molar, so that is here on the third column. Okay. 1, 2, 3. Okay, so on this column, we have the 0.01 molar. Okay, so tama. So let's look for calcium 2 plus. Okay, so calcium is here. What will be the corresponding gamma for calcium if the ionic strength is 0.01 molar? So according to the table, that's 0.675. So that is the gamma value already. 675. So we don't need to use the Debye equation anymore as long as the ionic strength is written here. No, it is within this range and that number. Okay. But for ionic strength greater or beyond this range, then you have to use the Debye equation. Okay. Okay. So this equation will only work at this limited range. Okay. Beyond that, you have to use the Debye equation. And lucky for you, most of the problems here in the quiz and in the examination have ionic strengths around these values. Okay. So yan. So good lucky for you because you don't need to use the Debye equation anymore. Although I will give you some questions that will require the use of that equation. Okay, so that will be on your quiz next week. Okay, so what if the activity coefficient is the between your values in the table? Okay, so suppose our mu here is 0.025 molar. As I told you, you can use this table as long as you are within this range, but 0.025 molar is not written here. Okay, 0.025 molar is not written on this table. But I told you, you can use this table as long as it is within this range. Now, how? How to solve? How am I going to solve for the activity coefficient if that is between the ranges shown here on this table? Okay, so let's look first. Where is 0.025? Okay, so 0.025 is somewhere between here. Okay, that means the gamma value is somewhere in between these two numbers. Okay, so we can use linear extrapolation to determine what will be the value of gamma within this range. Okay, between this. Okay, so in order for us to do the linear interpolation of gamma, if our ionic strength is between whatever is written on the table, this is how you're going to do it. No? So you list down the gamma and the mu starting from the lowest range. So the lowest range here is the 0.01. Okay, so this will be our limited range. So the lowest will be 0.01. Okay, and the corresponding, ay, mali. Dito pala yan. So the lowest ionic strength between our range is 0.01 molar, and the corresponding gamma for H plus is 914. Okay, 0.914. And then we have our unknown. I don't know what the gamma value is, so we're going to solve for that. And then the highest range, now the highest range is 0.05, and the corresponding gamma value at 0.05 is 0.86. So actually, we can use the Debye-Yucal equation naman, but I don't want to use it because I told you that as long as your as long as your ionic strength is within that table, then you can you can maximize the use of that table now. So I'm not going to use Debye-Yucal, although that will be more accurate, but I don't want to use it because the equation is dreadful. Okay, so I want to make things. I want to maximize my table. Okay, so for you to solve for the for the gamma, if your ionic strength is somewhere in between what's written on your table, you have to list down your three mu's. No, you have to list down your three ionic strengths and their corresponding gammas. Then the equation to be used for linear interpolation is this: the unknown y interval divided by delta y, and the known u interval divided by the delta mu. Okay. So what is the unknown gamma interval? So the unknown gamma interval is the difference of the largest and the x, no, or your gamma. So suppose this is our unknown gamma interval. So that will be our unknown gamma interval. The known mu interval would be this one also. Okay. So again, this will be our unknown gamma interval. Okay, so you can use this one here sa baba. You can use this. However, I want to use whatever is written on the top. Okay, so this is our unknown gamma interval, and the corresponding group, no, on the other column will be the known mu interval. Okay, and how about the delta y? So again, they are highlighted in blue. For the delta y, that is the entire range. Okay, so they are in red brackets. So that's the difference between the two ranges. Okay, so let us plug in whatever the number is in our equation. So for the unknown gamma interval, that will be 0.86 minus the gamma, or x. And for delta gamma, that is this minus this. Okay, so that would be 0.86 minus 0.914. Okay, so again, the unknown gamma interval is this one, and the delta gamma is the entire range. For the known mu interval, this is this minus this, okay? And that is 0.05 minus 0.025. And that's divided by delta mu, so that is the one in the red bracket. That is 0.05 minus 0.01. Okay? You can use the shift solve function of your calculator to solve for the missing gamma. Okay, so you can use the shift solve function. So I'm not going to show the algebraic derivations. Okay, so I'm going to use the shift solve function of the calculator to make things faster now. Okay, so shift solve, gamma is now equal to 0.894. Okay, so as long as your ionic strength is between whatever is written on the table, you can use linear interpolation. Okay, and yan. Use this equation, use this pattern, okay, to solve for the unknown gamma value if the ionic strength is within the ranges shown in the table. Okay, so that's how we use the table presented by Kieland, no, to solve for the ionic strengths. The activity coefficient. Okay, so please maximize the use of this table. Okay, but again, if your ionic strength is beyond the range shown here, if it is less than this or greater than this, then you cannot do the linear interpolation anymore. You have to use the Debye-Uckel equation. Okay, so with that, we are done with our session today. So next week will be asynchronous so that you will have more time to prepare for the upcoming assessments, especially the midterm. Okay, so for our asynchronous session, I will show you how to apply the concept of activities and the activity coefficient in solving for equilibrium problems. So I will answer these problems on that asynchronous session. Okay, so I will upload the video in which I'm going to answer all these 6 items, uh, showing the application of this topic in equilibrium calculations. Okay, so that will be all for our session today. Hopefully, to be honest with you, no, during my undergrad, this was actually a very hard topic to grasp. No, however, um, the good thing with your mode of learning today, you can rewatch the video multiple times, no, so that you can grasp the knowledge, no. So hopefully, if you watch this video for the second time, the third time, no, you will get it, no. Okay, so this is quite a difficult topic, but no, it is manageable naman, no? And also, whatever our calculation is for this topic, that will not be applied on future topics. Okay? So, hanggang dito lang yung calculation na to. So for the next topics, we're going back to the usual equilibrium equations. Okay. So we're going back to the simplified versions. Okay. So that will be all for our session today. So thank you for attending. No? And again, next week will be asynchronous meeting. No? So asynchronous so that you will have more time to prepare for the midterm exam. I will upload more materials on this chapter, okay, to help you with your review. Okay. The video will be uploaded, uh, the video for the discussion part of the calculations will be uploaded early next week. No? So most likely Monday. No? Okay. So hopefully um, you will be able to catch up with the calculations. No? Madali lang naman. Okay. So that will be all for our session today. So thank you for your attendance, and I'll see you again um, after the consultation week. So next week, no meeting. Next week, midterm exam. Next week is a consultation week. So most likely the next class session will be around April na. Okay, because we have Semana Santa by the last week of March now. Okay, so yeah, so I'll see you again around April now. So that will be all for today. A copy of the class recording will be uploaded on YouTube. Now please tell your classmates who are not around that this topic is quite hard, but it is manageable. Okay, so ganun na lang. So again, a copy of the video will be uploaded on YouTube for their reference. Thank you for attending. I hope you have a